In our lesson today, I would like to talk about the analysis of dimension. So, in analyzing dimensions, there is some of the terms used in doing that I would like to say before we start doing some calculations on that regard. So, basically, the three fundamental quantities that we use in analysis of dimension is length, mass, and time. When you look at the length is represented with a capital letter, mass is represented with a capital M, and time represented with a capital T. So these are the basic fundamental quantities that we are going to be using to analyze any derived quantities. So in analyzing that, what we are trying to do is that we are trying to bring down all the derived quantities into their what? Into their derivatives, which is the fundamental quantities or other quantities that made up that derived quantities. So, and that is what we are going to be analyzing. So I am going to use these few examples to show exactly what we are talking about. Now, let us analyze area. So what is the dimension of area? Originally, before you can answer that question, you must know the derivation of area or the definition of area. So already we know that area is equal to length multiplied by breadth. So if we know this, then how do we now bring down this length and breadth? So we can now see that area is equal to length times breadth. So we can see that L is already here, but B is here. So, but already we know that breadth is equally length, but a shorter length when we talk about the dimension of area and breadth. So it's just a description of the difference between a longer length and a shorter length. So what I am saying in earnest is that the breadth is actually another length. So representing that, we now have L multiplied by L, and that gives us what? L raised to power 2, or L squared. That is the analysis of dimension. So area is given as the L square as the dimension. Now, I am going to make you understand what are those things that you are going to see, and then you now say, yes, this is supposed to be represented with L. So you can see I have represented breadth with length. So I am equally going to represent height. Height is equally represented as L. So another one is distance. Distance is represented with what? L. They are all talking about what? The distance between 2 points. So another one is displacement. So whenever you hear displacement, so it equally represents what? L dimensionally. So these things are what you are going to be looking out for when analyzing dimensions. So whenever you see it, you are going to understand, yes, they are going to be represented with what? Remember, they are one, breadth, and then two, height, three, distance, and then, of course, displacement. So they are what you are going to be using to represent with what? Now, coming to velocity, let us analyze velocity and see the dimension of velocity. So velocity is displacement over time. So that is why the understanding of these derivatives or dimensions are very important, because if you can't define what velocity is, there is no way you can analyze it dimensionally. So if we define velocity as displacement per unit time, so that means already from what I have listed here, you can see that displacement is there, and we are going to replace it with what? L. And then time is equally there, and time is replaced with what? A capital T. So I now have L over T. So from our indices rule, we know that L over 1 multiplied by 1 over T, if something is like this, then it is the same thing as L T raised to power minus 1. So, and this is the dimension of the velocity. Okay, I will do that for acceleration. So acceleration, what is acceleration? So acceleration is velocity change over time. So acceleration is velocity change over time, which is v over t. Now, look at this now. I am going to do v over t. So you can see t is in dimensional form, but v is not. So what I am going to do is that I am going to do 1 over t, then multiply by v. I am going to define v. So v is displacement over time. So I'll now do 1 times L is what? L. And then T times T is going to give T square. And then using indices rule, I am now going to have that LT raised to power 2. And that gives me the dimension of the acceleration. Okay, and then finally, let us look at the pressure. How do we analyze pressure? So what is the meaning of pressure? What we are going to do. How do we define pressure? So pressure you need to know that is force over area. Force over area is pressure. So pressure is equal to force over area. So what is force? So when you look at force and area, none of them is represented in dimensional form. I mean length, mass, and what? And the time. So we are going to define all of that. So defining the numerator, which is force. So we say that force is mass times acceleration over the area. Area is length times what? Length, or length times breadth. And breadth is represented in dimensional form as L. So looking at this, we can now see that I have M as in dimensional form. I equally have L times L in dimensional form. So that means we are going to do M over L square, then multiply by what? A. So because acceleration is not in its dimensional form. So what I'll do next is I'll now do M over L square. Then I'll now define acceleration as velocity change over time. Okay, so doing that, we can now bring down this in the same position, and then I have M over L square, then T. Then I will define as velocity as displacement over time. Okay, coming down here, I will multiply the numerator. I will have ML all over L square T multiplied by what? T. So I have 1L, 2L here. I will cancel 1L. Then I am left with 1L. Then I will cancel 1L here. I have 1. So I am now left with only M in the denominator and the numerator, and then L T square in the denominator. And then taking the indices rule again, I have M L raised to power 1 T raised to power minus 2. And this is the dimension for pressure. So it is very important you understand these definitions of the derived quantities, so you can easily analyze whatever quantity you want to do. Thanks.